Everything you need to know about printed circuit boards, PCBs. A printed circuit board, PCB, is a critical component in electronic devices and serves as a platform for connecting and supporting various electronic components. PCBs are essential in modern electronics because they provide a way to efficiently and reliably interconnect electronic components and create complex electronic circuits. Here are the key elements and functions of a PCB. In the context of electronics and printed circuit boards, PCBs, the term substrate refers to the base material on which the PCB is constructed. The substrate serves as the foundation for the entire PCB and provides several important functions. Mechanical support. The substrate offers structural support to the PCB, ensuring that it maintains its shape and integrity. It helps protect the fragile components and conductive traces from physical damage or stress. Electrical insulation. Substrates are typically insulating materials that do not conduct electricity. This property is crucial because it prevents unintended electrical connections or short circuits between the various components and traces on the PCB. Thermal management. Substrates can influence the thermal properties of the PCB. Certain substrates may have better or worse heat dissipating properties, which can impact the PCB's ability to manage and dissipate heat generated by electronic components. Common materials used as substrates for PCBs include FR4, flame retardant. For this is a widely used substrate material made from layers of fiberglass cloth bonded together with epoxy resin. FR4 is known for its excellent electrical insulation properties and mechanical strength. FR1, FR2, FR3, these are older and less common substrate materials compared to FR4. They are similar to FR4 but may have different properties. Metal core PCBs, MCPCBs. In some applications where efficient heat dissipation is critical, such as LED lighting and high-power electronics, the substrate may consist of a metal core, typically aluminum or copper. This metal core helps spread and dissipate heat more effectively. Ceramic substrates. Ceramic materials, like aluminum oxide, Al2O3, and aluminum nitride, ALN, are used in specialized applications where excellent electrical insulation and thermal conductivity are required, such as in high-frequency RF circuits or power electronics. The choice of substrate material depends on the specific requirements of the PCB's intended application. Different substrates offer various advantages and disadvantages in terms of electrical performance, thermal management, cost, and manufacturability. Designers must carefully select the appropriate substrate to ensure the PCB meets the needs of the electronic device it will be a part of. Copper layers are a fundamental component of a printed circuit board, PCB. They play a crucial role in forming the conductive pathways that connect various electronic components and create electrical circuits on the PCB. Here's more information about copper layers in PCBs. Conductive pathways. Copper layers serve as the conductive pathways that carry electrical signals and power between different components on the PCB. These pathways are created through a process known as copper etching, where unwanted copper is removed to form the desired circuit pattern. Copper thickness. The thickness of the copper layers can vary depending on the PCB's design and intended application. Common copper thicknesses for PCBs include 1 ounce, 1 ounce, 2 ounces, 2 ounces, and 3 ounces, 3 ounces per square foot. Thicker copper layers can carry more current and dissipate heat better but may also increase the cost and complexity of PCB fabrication. Layer types. PCBs can have single-layer, double-layer, or multi-layer copper configurations, depending on the complexity of the circuit. Single-layer PCBs have one copper layer on one side of the substrate, while double-layer PCBs have two copper layers, one on each side. Multi-layer PCBs have more than two copper layers sandwiched within the substrate, allowing for complex and compact circuit designs. Inner copper layers. In multi-layer PCBs, there can be multiple inner copper layers between the top and bottom layers. These inner layers are interconnected through vias, small holes, drilled through the substrate. They enable complex, multi-dimensional circuit connections. Copper pour. Copper layers can be solid, where all of the copper is etched away except for the desired traces, or they can be used for copper pores. Copper pores involve filling large areas of the PCB with copper, which helps to reduce electromagnetic interference (EMI) and improve grounding. Ground and power planes. In multi-layer PCBs, some copper layers may be dedicated to ground planes or power planes. Ground planes help establish a common reference voltage for the circuit, while power planes distribute power to various components efficiently. Trace width and spacing. The width and spacing of copper traces are critical design parameters in PCB layout. They determine the current carrying capacity, impedance, and signal integrity of the PCB. Designers must carefully choose these parameters to meet the circuit's requirements. Copper layers are an essential part of PCB design and manufacturing. The design of the copper traces, their placement, and the selection of copper layer thickness are all critical factors that influence the performance, reliability, and functionality of the electronic device in which the PCB is used. Proper attention to copper layer design is essential for ensuring the PCB functions as intended. Traces and pads are integral components of a printed circuit board, PCB, and play a crucial role in connecting electronic components and creating functional electrical circuits. Here's an overview of traces and pads in the context of PCB design. Traces. Definition: traces are thin, narrow conductive pathways or tracks on the surface of a PCB substrate. They are typically made of copper and serve as the routes through which electrical signals and power flow between various components on the board. Function: traces connect different components on the PCB, enabling the exchange of signals, data, and power. They form the conductive wires of the circuit, ensuring that electrical connections are established as intended. Design considerations: the width, thickness, and spacing of traces are crucial design parameters. These parameters are chosen based on the current carrying capacity, impedance requirements, and signal integrity considerations of the PCB. Wider traces can carry more current, while narrower traces may be used for signal lines. Pads. Definition: pads, also known as solder pads or landing pads, are flat, typically circular or rectangular areas on the PCB surface. Pads are designed to provide a place for electronic components to be attached or soldered to the board. Function: pads serve as connection points between the electronic components and the PCB. Components like resistors, capacitors, integrated circuits, connectors, and other discrete devices are soldered onto these pads to establish electrical connections. Types of pads: there are different types of pads, including through-hole pads, used for components with wire leads that pass through holes in the PCB, allowing them to be soldered on both sides. Surface mount pads, designed for components with surface mount packages, where solder is applied to the pad surface, and components are placed on top. Thermal pads: these pads are used for components that require effective heat dissipation, such as power semiconductors. They are often connected to copper planes to help dissipate heat. Design considerations: the size, shape, and spacing of pads are important for ensuring proper component attachment and soldering. The design must consider the component's package type and lead configuration. Both traces and pads are designed and laid out using PCB design software, and their arrangement on the PCB is critical for the circuit's functionality and reliability. Careful consideration of trace widths, pad sizes, and spacing, along with adherence to design rules and standards, is essential to ensure that the PCB functions as intended and can be manufactured and assembled correctly. Vias are essential components in printed circuit boards, PCBs, that enable the connection of different layers of copper traces, allowing for complex, multi-layered circuits. Vias serve as electrical pathways, and they are crucial for creating intricate and compact PCB designs. Here's more information about vias. Definition: vias are small holes or openings that are drilled, etched, or mechanically punched through the PCB's substrate and are then plated with a conductive material, usually copper. These plated holes establish electrical connections between different layers of copper traces on the PCB. Types of vias. Through-hole vias: these vias pass entirely through the PCB, connecting the top and bottom copper layers. They are commonly used in double-sided and multi-layer PCBs. Through-hole vias are mechanically robust and provide good electrical conductivity. Blind vias connect an outer layer of copper traces to one or more inner layers but do not pass through the entire PCB. They terminate at one of the inner layers and do not extend to the opposite side of the board. Buried vias are entirely contained within the inner layers of the PCB and do not connect to the outer layers. They are used to establish connections within multi-layer boards without affecting the external appearance of the PCB. Functions. Interlayer connections. Vias allow signals, power, and ground connections to pass between different layers of a multi-layer PCB. This enables complex routing and minimizes the need for long, space-consuming traces on the PCB's surface. Signal integrity. Vias play a role in maintaining signal integrity by providing a low-resistance, reliable path for signals to transition between layers. Properly designed vias help avoid signal degradation. Heat dissipation. In some cases, vias can be strategically placed to enhance the PCB's thermal performance by improving heat dissipation from components to internal copper planes. Design considerations. Size. The size of vias, including their diameter and annular ring, the copper pad surrounding the via, is determined by the PCB design requirements, such as current carrying capacity and the spacing between traces and components. Placement. The placement of vias is critical to achieving efficient signal routing and thermal management. Designers must carefully plan via locations to optimize the PCB's performance. Annular ring. The annular ring is the copper area around the via's hole. It should be large enough to ensure a robust connection but not so large that it interferes with adjacent traces or components. Vias are a fundamental part of modern PCB design, allowing for the creation of high-density and complex circuits while minimizing the physical footprint of the PCB. Proper consideration of via placement, size, and type is essential for a successful PCB design that meets the electrical and mechanical requirements of the electronic device it serves. Solder mask, also known as solder resist or solder stop, is a protective layer applied to the surface of a printed circuit board, PCB, to insulate and shield the copper traces and pads from environmental factors and unintended soldering during the assembly process. It is an essential part of PCB fabrication and serves several important functions. Protection from environmental factors. Solder mask provides a protective barrier that shields the exposed copper traces, pads, and vias from environmental elements like moisture, dust, and contaminants. Without solder mask, these elements could corrode the copper over time, leading to electrical issues and reduced reliability. Preventing short circuits. Solder mask helps prevent unintended electrical connections or short circuits between adjacent copper traces or pads. It does this by covering the areas of the PCB where soldering is not intended, ensuring that solder only adheres to the designated pads during the assembly process. Improved soldering. Solder mask defines the precise areas where solder should be applied during the soldering or reflow process. This helps ensure that components are correctly aligned and soldered to the PCB, reducing the chances of solder bridges, unwanted connections, between closely spaced pads. Enhancing signal integrity. By preventing solder from wicking along traces, solder mask can improve signal integrity by maintaining consistent trace geometry and preventing solvent-induced changes in trace impedance. Identification and aesthetics. Solder mask is typically applied in different colors, commonly green, but also available in other colors, and may include silkscreen markings, labels, and component outlines. This aids in component placement, identification, and assembly. Thermal protection. Solder mask can provide some level of thermal insulation, which can be useful in high-temperature applications or excessive heat from nearby components might damage the PCB or its components. Solder mask is typically applied using a liquid photoimageable solder mask, LPSM, or dry film solder mask, DFSM. The application process involves exposing and developing the solder mask material to define the desired areas for solder mask coverage. The areas to be protected are masked, and the remaining solder mask material is cured or hardened. Designers must consider the solder mask layer when designing the PCB layout, as it affects the spacing between traces, the pad size, and the overall design of the board. Properly applied solder mask is essential for the long-term reliability and functionality of PCBs in electronic devices. Silkscreen, in the context of printed circuit boards, PCBs, refers to a layer of markings, labels, symbols, and text that is printed or applied to the surface of the PCB. The silkscreen layer is typically placed on the top and or bottom of the PCB and serves several important purposes. Component identification. Silkscreen markings are used to label and identify various components, such as integrated circuits, resistors, capacitors, connectors, and other electronic parts. These labels make it easier for technicians, assemblers, and repair personnel to identify and place components accurately during PCB assembly and troubleshooting. Reference designators. Each component on the PCB is assigned a reference designator, such as R1 for a resistor or U1 for an integrated circuit. The silkscreen layer often includes these reference designators alongside the corresponding component locations to assist in component placement and circuit debugging. Polarity and orientation. Silkscreen markings can indicate the correct orientation and polarity of components that must be placed in a specific direction, such as diodes, LEDs, and polarized capacitors. This helps ensure that components are installed correctly. Assembly instructions. Silkscreen may include assembly instructions, guidelines, or warnings for PCB assembly and handling. These instructions can help avoid common assembly mistakes and ensure the proper operation of the electronic device. Company logo and part numbers. Some PCBs include the manufacturer's logo, part numbers, revision information, and other branding details on the silkscreen layer for traceability and quality control purposes. Testing and quality control. During the manufacturing process, test points and test access points may be indicated on the silkscreen layer. This helps test equipment operators connect probes or test points for functional testing and quality control. Aesthetics. Silkscreen can also contribute to the visual aesthetics of the PCB, making it more visually appealing and professional looking. Silkscreen is typically applied using silkscreen printing techniques, although other methods like inkjet printing or machine-applied labels may also be used. The ink or marking material used for the silkscreen layer is typically white, but other colors can be used for aesthetic or functional purposes. Designers and PCB manufacturers work together to create the silkscreen layer in a way that enhances the usability of the PCB and ensures that critical information is readily accessible to those involved in the assembly and maintenance of the electronic device. Properly applied and well-designed silkscreen can greatly assist in the efficient and error-free assembly and servicing of PCBs. PCBs come in various types, including single layer, 1 copper layer, double layer, 2 copper layers, and multi-layer, more than 2 copper layers, PCBs, depending on the complexity of the circuit. Multi-layer PCBs are common in modern electronics, where space is limited, and numerous components need to be interconnected. The design and manufacturing of PCBs involve specialized software for schematic design and layout, followed by the fabrication process, which includes etching copper traces, drilling holes for vias, and applying protective layers. After fabrication, electronic components are soldered onto the PCB, and the entire assembly is integrated into electronic devices. PCBs play a crucial role in the functioning of a wide range of electronic devices, from simple consumer electronics like smartphones and computers to complex systems like medical equipment, aerospace technology, and automotive electronics. Their design and quality are essential for the reliable and efficient operation of these devices.